All right, today's a wonderful day because we get to do practice involving the derivative of the inverse trig functions. Hello, arctangent! Woo! Arctangent's in the house! So I am looking forward to today. And of course, I hope you're looking forward to today too. As always, it's important that you do as much of these practice problems as you can by your own first. And so you can use the videos to help you get unstuck or maybe see an alternative point of view. Make frequent use of the pause button. If you're working along on a problem, then you're like, well, let me see. That's what I need to do next. Okay, then pause and work it out on your own. The more problems that you do today, they're going to set you up for future success. And the more problems you'll be able to do in the future. And isn't it great to be able to solve problems? I think it is. All right, well, let's get going. So the first problem really is about just practicing our basic derivatives. Now, most of these involve arctangent, but we have this derivative of log of 1 plus x squared. So it might be helpful for reference to remember that we have the derivative of arctangent. So we'll write it down here for our reference. So the derivative of arctangent of x is 1 over 1 plus x squared. Okay, so let's think of the derivative of natural log of 1 plus x squared. A lot of people tend to sort of mix these together because what happens? Well, if you think of the derivative of natural log of 1 plus x squared, the way that derivative of a log works, it's 1 over the inside, right? So, derivative of natural log, 1 over the inside. And if we stopped here, we wait, that shouldn't be right. And it's not. What are we missing? Okay, so what we're missing is the chain rule. So the chain rule says you multiply it now by the derivative of the inside. What's the derivative of 1 plus x squared? Well, the answer is 2x. Now, still, you see that it has a vague resemblance between the derivative of arctangent and the derivative of natural log of 1 plus x squared. But there is a distinction. And that's an important distinction, so it might show up in the future. And things like this tend to show up, especially as we head into towards calculus 2. Good stuff coming in the future. Now, for the rest of these, we can actually make things a little bit simpler by noticing what's going on. We really have an arctangent of a function in all of these. So what we can do is we can say, well, what's the general rule? I know how to handle the derivative of just arctangent. So what we can do is write down the general rule. The derivative of arctangent of some function would be what? Well, what we have is if we think about what's going on just in the line above, it says, look, here's what you're plugging in, and that shows up into there. So if we think about the chain rule, well, what we do is we say you take the derivative of arctangent, but instead of plugging x in, you plug in f of x. So what we would do here is we would plug f of x into that slot. So it would be 1 over 1 plus, add some parentheses so we don't miss anything, squared. Then times by, on the outside, the derivative of f of x, f prime of x, which you can write as f prime of x divided by 1 plus f of x quantity squared. So if we remember that rule, it's actually pretty quick to go through and do these problems. So let's see how we do. So we start with our b. All right, arctangent of sine. Well, what would that be? So the rule says you're going to take 1 over 1 plus the inside function squared. So our inside function is sine. So 1 over 1 plus sine squared of x. Well, that's not always the best notation, but it is legal notation. And now, don't forget, times the derivative of the inside, that's like the f prime of x here, so times cosine x. Now, what do you do with 1 plus sine squared of x? The answer is, we leave it alone. There isn't a nice identity with 1 plus sine squared. If it was, say, 1 minus sine squared, there's stuff we could do. But 1 plus, it's different. So, all right, good. Well, let's try another one. Okay, part C. Arctangent of x squared. So what would that be? 1 over 1 plus x squared squared, right? So it's 1 over 1 plus whatever you have on the inside squared, times by the derivative of the inside. So times 2x. So we could write that as 2x over 1 plus x to the fourth, because x squared squared is x to the fourth. Now, let's go to our next one. Okay, root x. Well, first off, let's recall that if we're trying to write things in a more calculusy way, we can also write that as arctangent of x to the 1/2. So square root of x, if you convert to x to the 1/2, it works better for our rules where we think of x to a power. So if we follow our rules, that's 1 over 1 plus whatever's on the inside squared. Well, what's on the inside? X to the 1/2. So x to the 1/2 squared times the derivative of the inside. So then multiply by the derivative of the inside. So that would be 1/2 comes down, x to the minus 1/2 power. All right, well, what is that? Well, we can write that as 1 over, here, x to 1/2 squared would be 1 plus x. This half I can put as a 2 in the denominator, and then this x to minus 1/2, that really means we have a square root of x downstairs. And there we go. So that's what the derivative looks like. All right. Now we could do some various things. We could multiply the square root of x through, but it is what it is, right? Okay. Well, let's finish it up, right? It's a good thing to do. So how about arctangent e to the x? Well, 1 over 1 plus the inside squared times by the derivative of the inside. And remember, it's not this denominator taking derivative, no, just the inside piece, the e to the x. Derivative of e to the x is e to the x. And we can simplify that as e to the x over, and e to the x squared is really the same as e to the 2x. So that's sometimes how you'll see that. So the ability to move between e to the x quantity squared and e to the 2x can be really useful in solving some problems. So it's good to be able to master that art. All right. Well, let's try another problem. So, we're given a function. It's h of x, and it's 3 times the natural log of 1 plus x squared plus 8 times arctangent of x. And we're asked to find all values of x where the second derivative equals 0. Now, initially, the function looks really kind of messy. It's like there's natural logs and arctangents mixing together, and if we had to try to understand that function, we would struggle because they are not very clean functions to be working with. But that's not the function we need to set equal to 0. What we need to do is get to the second derivative. All right, so let's work our way there. So we'll start with our function h of x is 3 natural log of 1 plus x squared, and then plus 8 times arctangent of x. So there's our first function. Now, the first derivative. After all, if we're going to get to the second derivative, we've got to start with the first one. So, the natural log of 1 plus x squared. So the rule is, whenever you have a natural log, 1 over the inside, so 1 over 1 plus x squared, times the derivative of the inside. Well, the derivative of 1 plus x squared, 2x. And arctangent of x, well, that's what we just learned. Derivative of arctangent of x, 1 over 1 plus x squared. Now, we have to take another derivative, but I think this is a case where it makes sense because I see that both of the terms involve a denominator with 1 plus x squared. Let's go ahead and move things together because I think it would be easier. See, oftentimes if you have to do something with a computation, simplify first. We're seeing there's another derivative to happen, so let's simplify before we take that next derivative. So what would we get? Well, common denominator is 1 plus x squared. And then the numerator, from the first term, you'd get 6x. And from the second term, plus 8. And now, that looks like a nice quotient. And notice that it's really a really nice quotient in the sense it's polynomial over polynomial. See, our initial function had a natural log and an arctangent, but when you take the derivatives, those become more rational functions to work with. So now we're ready for our second derivative. So, second derivative. So, let's go through the process. We take the bottom, 1 plus x squared, times the root of the top, which is 6, minus the top, 6x plus 8, generous use of parentheses, make sure you keep using parentheses, so times the root of the bottom, which is 2x, all over the bottom term squared. Good. Now, what's going to happen? We want to set this equal to 0. It's a good habit to get into, just sort of like kind of glance at the denominator and ask the question, do we need to worry about that? So let's ask ourselves the question, do we need to worry about that denominator? The answer is no, we don't have to worry. Well, for two reasons. The first reason is, if I want something to be 0, I really need a numerator to equal 0. But the other thing is to say, okay, look, the denominator down here, this is really nice in the following sense. 1 plus x squared is always at least as big as 1. So what that says is our denominator here is never 0. And that's good. When you can say for sure, hey, my denominator is never 0, I'm not afraid. That's good news for us. So our focus now transfers to the numerator. So let's see what we can say. So we need the numerator to equal 0. So let's multiply this out. So we need 6 plus 6x squared. Then distribute the 2x through. And don't forget the minus, that's important. Minus 12x squared, 6x times 2x, minus 16x equals 0. All right, so that's what we're up to. All right, let's clean up. So let's see. 6 minus 12 would give us minus 6x squared minus 16x, and plus 6 equals 0. Well, let's do a couple things. First off, they're all even numbers, so let's divide through by a 2. The other thing is that currently our leading coefficient is negative. Oftentimes it's easier for us, at least when we're trying to figure out how to do things, to make it positive. So I'm going to divide through by negative 2, which really means I'm going to flip all the signs. So we'll have 3x squared plus 8x minus 3 equals 0. All right, so good, we've made progress. And now we say, quadratics. We see a lot of quadratics, don't we? Yeah, well, I mean, they're good practice. And you might finish and say, boy, you know, calculus is all about solving quadratics. It's not only about solving quadratics, but it is useful to be able to solve quadratics. So, does this factor? Well, yeah, in fact, if we were thinking about how to factor it, there's a couple of clues. First off, there's not a lot of things you can do with 3. It has to be 3 and 1. And similarly, this has to be 3 and 1. And we say, well, because there's a minus here, that means they're going to have different signs. So we want a difference to produce 8. Well, notice 9 and 1, the difference is 8. Exactly. So, now we have a plan. So we're going to have 3x, and because we had to need the 3 times the 3, there needs to be a 3 here for the constant and an x here. Now we just have to think about the signs. They have to be different since that's negative. And then we say, all right, I need to end up with plus 8x, so I better make sure that the 9 is really large, positive, and then the other part is the negative. So if you're not sure, just check. 3x squared, then 9x minus x is 8x, and minus 3. Good. Equals 0. We're almost there. 0, our good friend. See, because we're in the situation. We have things multiplying together, and we get 0 out, which can only happen if one or more of the terms is 0. So we look at each piece and say, okay, when does 3x minus 1 equal 0? Well, you add 1 divided by 3, x equals 1/3. When does x plus 3 equal 0? If you subtract 3 across, negative 3. And therefore, at 1/3 and negative 3. Those are the two times where the second derivative equals 0. All right, good problem. Good stuff. Good stuff. Okay, next problem. So, we're given the implicit curve, arctangent of x squared minus y plus sine of 2x plus y equals xy plus 8, and we need to find the tangent line at the point negative 2, 4. Now the good news is we already have our point, so hey, we're halfway to our tangent line. So we mostly just have to focus on finding our slope. So that's good. Now we should, for sanity's sake, check, is this point negative 2, 4 actually on this curve? They said it was, but we should check. So let's check. Negative 2 squared is 4, minus 4 is 0. Arctangent of 0 is 0. All right. Then we have sine of 2 times negative 2, which is negative 4, plus 4, which is sine of 0. Okay, and sine of 0 is 0. So we get 0 plus 0 over here. Negative 2 times 4 is negative 8. And then plus 8 is 0. Okay, good. So it is the case that 0 plus 0 is equal to negative 8 plus 8. So the point is on the curve. Just nice to check. Probably wasn't required, but it's always good to check these kinds of things. Now, what's left? We need the slope. So, here we go. Now, notice what kind of differentiation tools are we going to need? Well, we're going to need to know the derivative of arctangent and sine and product, but there's another word, key word, right here, implicit. So that really says we need implicit differentiation. So remember, how does implicit differentiation work? Well, we look at this problem and we say to ourselves, I'm going to think of y as being a function of x. Now you might ask the question, could I think of x as a function of y? And the answer is yes, you can. So why do we think of y as a function of x? Well, because oftentimes when we're thinking about our slope, we really think of our slope as being dy dx. That's how we have it, because it's change in y over change in x. So it's dy dx at the point that we're interested in. So that's why we want to think of y as a function of x. We're taking the derivative with respect to x. So let's take our derivative with respect to x. So I'll write down our function again for reference. Arctangent of x squared minus y plus sine of 2x plus y equals x times y plus 8. So again, we're going to take the derivative of both sides with respect to x, and in our mind, we have that little thought bubble. Boop, boop, boop. Whenever I see y, it's really a function of x. So the derivative of arctangent is 1 over 1 plus the inside squared. Then we're going to multiply that by the derivative of the inside. Well, the derivative of x squared is 2x minus the derivative of y is y prime. Okay, so y prime is shorthand notation for dy dx. Plus derivative of sine. Cosine. Inside stays the same. Then by the chain rule times by the derivative of the inside. So times derivative of 2x is 2. Derivative of y is derivative of y. Y prime. Equals. On the other side, start with the product rule. Derivative of the first times the second plus the first times the derivative of the second. So it'll be 1 times y plus x, y prime. And derivative of 8, 0. Goes away. Woohoo! It's gone. It's gone. Good. Now, what comes next? Well, we need the derivative at our point -2, 4. So what we're going to go is we're going to go through here, and everywhere we see an x, we're going to put a -2. So there's a lot of x's, so we're going to go ahead and just mark all those as -2. Everywhere where we see a y, we're going to put those as 4. Now notice I said y, not y prime, because y prime is what we're after. We're after the derivative. So let's see what happens. Well, good news is, notice here, you'll get -2 squared minus 4 is 0. That's 0 squared, which means that this whole first piece is just 1. Whew, easy. Good. So it's 1 times that, so this becomes -4 minus y prime. And then here we have 2 times -2 plus 4, which is 0. Cosine of 0 is 1. So then we have plus, and here we'll have 2 plus y prime is equal to, all right, on the other side, what do we have? Well, we have a 4, 1 times 4, and then we have -2 y prime. All right, now, can we simplify anything? And what simplifies? Well, we can. See, look, there's a minus y prime and a plus y prime. Those cancel right away. Aha! Nice, nice. Then what else do we have? We have -4 plus 2 is -2. We can bring that -4 across. So we get that -2 y prime is equal to -6. And then divided by -2, we can say y prime is equal to 3. All right, now, what does that say? Well, that says our slope is 3. All right, so, good. Things simplified very nicely. Now, they won't always simplify quite this nice, but when it does, we should always be happy. And we're happy. Good, good. Now, we're not done because what do we need? We need the line. What we've done is we found the pieces to make the line. So the last thing is we take our slope and our point. We say, all right, if we combine this information together, we get y minus our y coordinate is equal to our slope, x minus our x coordinate. Well, we can rewrite that. So y equals 3x, and then minus a -2 makes a +2, times 3 makes +6, add 4 more, so 3x plus 10. And there's our tangent line that we need. Good. We found it. Woohoo! All right. Well, good problem. All right. Let's go on to the next problem. Okay. Find all horizontal tangent lines to y equals the natural log of x to the 6th plus 1 minus root 12 arctangent of x cubed. Now let's talk about horizontal tangent lines. What does that mean? Well, we kind of understand what horizontal means. It looks like this. What's true about horizontal lines? Well, they have 0 slope. It's not going, downhill. It's not going uphill. It's saying the slope is 0. Okay, so really we need to say, let's find all places where the derivative equals 0. All right, that's our first step. They might say, isn't that the whole problem? Let's come back to that. So first step, let's figure out where the derivative equals 0. So we should start by taking the derivative. All right, so whenever I have the derivative of natural log, it's going to be 1 over the inside, x to the 6th plus 1, times by the derivative of the inside, which would be 6x to the 5th. Okay, minus square root of 12. That's kind of a weird number. I wonder why that's there. Square root of 12. Okay, we'll come back and visit that one. So arctangent of x cubed. So the way we do arctangent, 1 over 1 plus x cubed squared, right? 1 over 1 plus the inside squared times the derivative of the inside. So times 3x squared. Okay, well, let's see. Interesting. So what do we see? Well, we can write this as 6x to the 5th over x to the 6th plus 1. Now, if we think about square root of 12, what's true about square root of 12? Well, square root of 12 has a square in it, right? 12 is 4 times 3. So we can make a little side note here and say, hey, this is really 2 times square root of 3. And if we make that little side note, we say, look, 2 times 3 would make this a minus 6 times square root of 3, and then times an x squared. And that's over 1 plus x to the 6th. Hey, these are the same denominator. All right, let's put them all together then. And in fact, while we do that, let's clean up the numerator. So 6 is common. What else is common? The other thing that's common is the x squared. So we get x squared, and then we're left with x cubed, and then minus square root of 3. Good. So now what's left? Well, we need to know when is this equal to 0. So we set this equal to 0. The denominator will never be 0. X to the 6 is always greater than or equal to 0, and 1 plus makes at least 1. So we don't have to worry about any potential division by 0 headaches. So we look upstairs. Well, that means we really need to have that 6x squared times x cubed minus square root of 3 equals 0. Well, that could happen if the x equals 0, okay, or if x cubed is the square root of 3. Or if you like, we could say that x is equal to, by the way, square root of 3 is 3 to the 1/2. Take the cubed root, so that would be 3 to the 1/2 to the 1/3, which is 3 to the 1/6. All right, now, are these our answers? And why not? Now, you're probably like, well, they're not our answers because you just said it in a mysterious way, and why not? Okay, you're right, they're not the answers. But it's not just because I said it in a mysterious way. Something is afoot here. What are we asked to find? We're asked to find the tangent lines. See, specifically, find the tangent lines. What have we found? Are these tangent lines? The answer is no, they are not. What we found is these are the locations of where the tangent points are. So locations of the tangent lines. So in other words, if I were looking at this function, I would say, which part of the function should I look at to find these horizontal tangent lines? I would say, well, look at x equals 0. X equals 0, and x equals the 6th root of 3. Those are where you should look. So how do we find the actual lines? Well, the nice thing is if I have a horizontal line, it's actually pretty straightforward to find the line. All I have to do is figure out what's the height. So to finish off, we need to plug in 0 and the 6th root of 3 back into our function. So let's see what happens. At x equals 0, what do we get? We get y equals the natural log of 0 to the 6th plus 1, and then minus root 12 times arctangent of 0. Well, log of 0 to the 6th plus 1, that's log of 1. That's equal to 0. Arctangent of 0 is also equal to 0, which means we get 0. what happens at our other place? X equals 3 to the 1/6. Well, we get natural log. So I have 3 to the 1/6 power, and then I raise it to the 6th power. Well, that'll become 3 plus 1. Then minus root 12. Then we have arctangent of 3 to the 1/6 cubed. Well, really, see, look, we know what x cubed is. It's 3 to the 1/2. So it's square root of 3. Now, can we simplify? Well, 3 plus 1, we can do that. That's equal to 4. Okay. How about arctangent of root 3? Do we know what that is? Well, does somebody know what it is? In fact, this turns out to be one of the values that we do know. So, the question, is there some convenient angle where tangent of something is equal to root 3? Because if there were such an angle where tangent of that angle is root 3, then arctangent of root 3 is whatever this thing is. Now, if you're an arctangent devotee, like some of us are, you might know this off the top of your head. I will say that there are certain angles you should know. For instance, arctangent one you should know by heart is pi over 4. If you don't know the following, it's okay. And that is that arctangent of root 3 is 60 degrees, but of course we do calculus, so we call it pi over 3. It's actually a nice angle. So 0, 1, root 3, infinity, whatever that means, infinity. They all have nice answers, as does 1 over root 3. Okay, so anyways, what does that leave us with? Well, it leaves us with natural log of 4, and then we can do the same thing we did before, right? Square root of 12 is really 2 times square root of 3, and then times pi over 3. And you can actually combine these three together, and you could write this as natural log of 4 minus 2 pi over root 3 if you wanted to, if you were so inclined. Okay, so we're almost done because we found out what's the y-coordinate when we plug in 0 and 3 to the 1/6. But since we know our slope is 0, all we need is the y-coordinate. And therefore, our desired horizontal tangent lines are y equals 0 and y equals natural log of 4 minus 2 pi over root 3. All right. You know, we may have guessed y equals 0 at the start, but I don't think we would have guessed natural log of 4 minus 2 pi over root 3 at the start. But we don't have to guess, right? That's the whole point. We have ways to find these things. We have ways, don't we? Okay. One more problem. Okay, so find the derivative of tangent of arcsecant of x. So I guess this is the one problem which we won't have arctangent on. But let's do the problem and see where we get. Okay, so it's a chain rule, right? Because we have tangent is the outside function, arcsecant is the inside function. So according to the chain rule, that would be what? Well, take the derivative of the outside. Derivative of tangent is secant squared of the inside stays as it is, arcsecant x. Times that by the derivative of the inside. Now, do you remember the derivative of arcsecant? Hopefully, I mean, we just learned it, right? So hopefully you know it. It is 1 over x square root x squared minus 1. All right, well, that was pretty quick. There must be more here to talk about. There is. Okay, first off, let's talk about this piece. This is really secant of arcsecant of x squared. Now, if you take secant of arcsecant of something, what do you end up with? So it's the inverse function. You know, when you do the arcsecant, it goes one way, secant pulls it back. And so this part here becomes x. And so it's squared. So really what the first part here, this whole first part, is x squared. And then we still have that second part, x square root of x squared minus 1. And then we say, hey, wait, the x's can cancel. And therefore, we have x divided by the square root of x squared minus 1. Okay, so that's the answer. But I still have a lot of space left. Let's do it again. Now you're probably thinking, why do it again? Let's do something before we do it again. All right. So we need to start thinking about what things are. So let's talk about tangent of arcsecant of x. The first thing we have to understand is what kind of thing is arcsecant. And you might say, well, is an arcsecant an inverse trig function? And yes, that is that's true. What I'm trying to get at, though, is what kind of thing is coming out of the arcsecant function? In other words, what is the output? Now, this is an important idea. Think about the trig functions. What kind of things do you put into a trig function? So if I have a trig function and I put something in, the way I think about what I'm putting in is I'm putting in an angle. So if I'm looking at an inverse trig function, the question about what comes out of an inverse trig function is the same as what goes into a trig function. So since we put an angle into a trig function, this output from arcsecant is an angle. So let's give it a name. We'll give it a very, very angle-like name. We'll call it theta. And, well, because the Greeks, they did a lot of stuff with geometry, so we tend to use Greek letters. So we have that arcsecant of x. We're calling it theta. Now, let's take the secant of both sides. Why? Because that would free up the x. That tells us that secant of theta is equal to x. Now, get ready. This next part is going to make you go, whoa. Ready? Here we go. Which is x over 1. Whoa. And I know you're not impressed. But this is so cool. Okay, what's happened? See, what's cool about trig functions is if you think in terms of triangles, because there are two ways to think about trigonometry. There's these circles and there's triangles. When you think about trig functions in terms of triangles, they're as ratios. So when we write secant of theta is x, that doesn't really click the ratio interpretation. But when we put it as secant of theta is x over 1, oh, there's a ratio now. So here we go. We draw a triangle. And here's such a triangle. It's not just any kind of triangle, of course. It's the right kind of triangle. It almost looks like I'm drawing a really bad 4. But all right, we'll put theta in a corner. And I know what you're thinking. Nobody puts theta in a corner. But we do. Yeah, it doesn't matter which corner, just any corner. Now we have to think about what ratio corresponds to secant. If you think about cosine, cosine is the adjacent side over hypotenuse. Now secant flips cosine. So secant is the hypotenuse over the adjacent. So we'll label the hypotenuse in x and the adjacent as 1. So you see in this triangle, the secant of theta is x over 1. What's this missing side? Well, Pythagorean theorem comes in. So we have that this side squared plus that side squared equals that side squared. So if you play around, it doesn't take very much, it would be the square root of x squared minus 1. Okay, so where are we going with this? Well, remember, arcsecant of x equals theta. So now let's look at this triangle and ask the question, what is tangent of theta? Well, tangent is opposite over adjacent. So this is the square root of x squared minus 1. So now, lo and behold, it turns out that the derivative of tangent of arcsecant of x is equivalent to asking the question, what's the derivative of the square root of x squared minus 1? In other words, tangent of arcsecant of x it can be simplified, is equivalent to this expression, the square root of x squared minus 1. All right, so we're almost there. Now, let's take this derivative. Fingers crossed, what should be true? It should be the case that they're the same. Okay, let's hope. Now, if we're going to take that derivative, we'll make it more calculus friendly. X squared minus 1 to the 1/2. So this would be the 1/2 comes down, x squared minus 1 to the 1/2 minus 1, which is minus 1/2, times by the root of the inside. So times by 2x. Now, what do you see? The half and the 2 cancel, and you're left with an x on the numerator. This minus half means the other term is downstairs, and it's a square root of x squared minus 1. They're the same. That shouldn't surprise us. We should get a consistent answer, but it's still nice when we do. It gives us a warm feeling of validation that we're understanding things. And isn't it great to understand things? Well, that keeps coming with practice, so keep doing that practice. Hope you have a great day.